maybe deposited to form the drain terminal. So please remember, one side you are trying to give the highly resistivity layer, and another side you are trying to deposit your metal layer. So please remember, that's why your impedance becomes much higher than the normal switches. And silicon dioxide is also treated here as another layer in order to go ahead with the fit metallic source and the gate terminal. All remember in your mind, is all parallel connections of all basic MOSFET cells or thousands of cells all together to form in the single chip of a silicon pattern. Please remember me. That's why silicon industries or silicon fabrication or micro electromechanical systems, MEMS fabrications are much vital in the society. Please remember. So all these combinations are connected in the variety of cells or constitute together on a single chip. That's why the MEMS will have a vital role in the society on various applications. And operations, there are two set of operations you will have: transfer characteristics, then drain characteristics, and output characteristics. So here, if you convert your gate circuit voltage becomes zero, obviously what will happen? The drain voltage will be present, because I told you earlier about two set of voltages, right? One may be the gate source voltage and another one may be the drain voltage. That means if you convert the gate source voltage to be zero, or a gate circuit voltage to be zero, automatically what will happen? The other voltage source will be present. Therefore, your N and P junctions are reversed bias. No current will be flow through the drain to source. This is one condition. And another condition in just vice versa. If you convert your VDD becomes zero, so that you will convert, you can make your gate to trigger, so that your gate voltage will have an effect. Thereby, the other side of effect will happen. Therefore, with gate voltage increase, current also increases as expected. Okay. And the MOSFET characteristics, the transfer characteristics and output characteristics. So there are two characteristics. One may be transfer characteristics and another one may be output characteristics. Transfer characteristics speaks about the drain current and the gate source voltage. The characteristic curve which draws between the drain current and the gate source voltage. And another one, output characteristics, which speaks about the drain voltage and the gate source voltage. The drain voltage with the, and also a gate source voltage, the variation on the drain current between these two sources. So this is the characteristic curve for your MOSFET transfer characteristics. So in the graph, you can see that the graph is between, the characteristic curve is between your gate source voltage VGS and also your ID. ID is nothing but drain current. Drain current is taken as amperes, and gate source voltages might be taken as millivolts. So there are a huge amount of current decay. That means you have a drain current amount get decreased at the level of 2 volt on the gate source voltage. When you keep your gate source voltage at the point of 2, or if it's less than 2, that means you are trying to reach to the steady state level. There are two level here. One may be your steady state and another one may be a transient state. That means here we are trying to find out the triggering between your gate source voltage and the drain current. And the MOSFET output characteristics, here the characteristic curves placed between your drain source voltage and the drain current, and also I told you another one, your gate source voltage. That means both the things are cumulatively considered here on the x-axis. Thereby you can able to find out how much amount of current may be drawn due to the ohmic effect which may place on the drain current. That means two set of sources I may have. One may be the drain source voltage, another one may be the gate source voltage. During that case, how my current will have a decaying amount of quality, that characteristics will give you the amount of relationship between the output characteristics. So output characteristics, there are three components. Please remember in your mind. Don't forget. And this may be the switching characteristics. The first graph will tell you about the instant on the time, the rise time up to T1. What is my steady state voltage? Then second one, there is a kind of slope between my gate source voltage and my drain source voltage. That means there is a huge amount of delay is required based on the triggering which you are trying to give. It depends on the triggering value, or depends on the pulses, or depends on the adjustment which I am making to trigger my gate. Thereby, I may have a delay to trigger on my gate. That period might be considered here as the duty cycle ratio, the T on divided by T on plus T of time. So with the help of that duty cycle ratio, I can able to find out my rise time and my delay time. And MOSFET applications, high frequency applications vary from few watts to few kilowatts. As I told you earlier, MOSFETs normally, I think last week classes while winding up, I told you, MOSFETs normally will have high switching losses. That's why we should not simply increase the MOSFET switches. Okay. For example, it's a single phase converter or a three phase converter. I should decide about that, how my bridge structure will be. Based on my bridge structure, I should decide about my MOSFET. But whereas in SCR, it's not like that. Okay. Whereas if you go for any inverter or converters, even in your rectifier circuit, I think which is available in your electrical lab, I think you might be visit. I don't know whether you visited or not. Maybe after you come to the campus, when you get a chance to visit the electrical lab, where you learn the drives and actuators, please check in the rectifier part. Most of the components occupied there are SCR, or the other name may be thyristors, which we discussed earlier. So here the output rating maybe varies from few watts to few kilowatts. MOSFET is normally wired in switch mode power supplies and inverters. So most of the inverters and even in your houses you may have your own inverter. But nowadays, whichever inverter you are using in the house, mostly it based on SCR based inverters. Please remember in your mind. Some earlier versions you might have the MOSFET version, but remember, you need not stick on to, when being a designer, you need not to stick on to a particular type. No, not like that. There is no constraint saying that we should go ahead with this type of component on this type of design fabrication on the inverter or converter. No, please remember. You should know the effective, you should know the basic functionality of inverter and converter, AC to DC conversion or DC to AC conversion. But these converting phenomena, according to the cost and according to the designing time and according to the commercial view to sell my product in the society, based on that, I can choose my switches. Please, that's why I told you, though there are a number of switches may be available, but being a designer, I should design about my product. That's what today morning the presenter told about that. There are a number of competitors, a number of designers, a number of people are available in and around the society. Your idea may be different, but I cannot steal from your idea. You may share your idea to me, but at the same time, when you have a clear idea and implementation structure towards the right perspective on the direction, then definitely I cannot steal into that. Please remember in your mind. Okay, that's what the morning actually I've attended many entrepreneurs, but morning quite it was interesting because in a lively way he told about the real facts which he faced from college days to till the implementation of BOS. Okay, so maybe you people get an opportunity to discuss with him, get this number and contact him and equip yourself to become the entrepreneur. So power supplies, the applications are like switch mode power supplies and the inverters. And the comparison, when we go for comparison, there are ups and downs in both the sides you may have, because BJT is another switching device and MOSFET is another one, metal oxide semiconductor field effect transistor, and BJ is a bipolar junction transistor. So bipolar device, unipolar device, one side will have low input impedance, and we all know that MOSFET is a high input impedance. And the high switching losses, but here also lower switching losses, but high conduction. Please remember, the third point here, it's mentioned low switching losses but high conduction. At the same time, if you increase the component, what I told you, you will have high switching losses, thereby your conduction losses becomes more and more. Please remember your mind. Okay, so that it may act as a voltage control device, MOSFET, and BJT may act as a current control devices. Secondary breakdown may be occurs here. Here also secondary breakdown does not occur here. At a certain level, you may have a breakdown voltage occurs, but here you don't have. But available with a rating of 800 amps up to 1200 volts, but here you may have with various rating like a 500 volt, 140 amps. That's why we may go ahead with a MOSFET like a SMPS, right? Okay, but BJT has the rating may be different. Yes, if you get an opportunity to open the cabinet of your CPU, if you have any old system in your house, you can very easily to identify the SMPS, switch mode power supply, how it is trying to give the instantaneous of amount of supply to the processor board on an instantaneous manner whenever the switching happens. And next to switch is called as IGBT, or insulated gate bipolar transistor. This is another type of IGBT switch or solid state switch. Maybe combining the best quality on the earlier two cases like what we discussed, BJT and MOSFET, and also this device also have high input impedance, okay, and low on-state power loss. Okay, the commercial names, maybe in the IGBT, there are a lot of commercial names in the society. So normally, when you go for electronic shop or to get some component, they may tell you the equivalent values. Will you agree or not? You may people have gone to any electronic shop then and there, right? By implementing your own module or small set of circuits or by repairing something. So that time, when you ask some specification, they may tell you that the corresponding equivalent of the other commercial products are available, but the same set of operation, no issue about that. Something like that, they may convince us. So the other commercial names are like SIGT, COMFET, then GMFET, and IGBT. These are all the various commercial names which are associated on your insulator gate bipolar transistor. So this may be the basic structure of your IGBT. You may have a gate terminal, you may have an emitter and a collector. So there are three terminals, and here this is the basic structural inner configuration of your IGBT. So between your gate and emitter, you have a gate voltage. Then between your gate and your collector, you have a collector voltage terminal and also the load. Please remember in your mind. So don't forget about that. So between your gate and emitter, you have a gate voltage. Then again, your emitter to collector, you have two things. One may be the collector voltage or the main voltage source, and maybe the load. The load may be connected between your emitter to collector region on the left side. And in the top layer, you may between your emitter and gate, you have a gate voltage. So there are two voltage sources here. And this may be the corresponding equivalent inner configuration of your IGBT. But by schematically, if you see this diagram internal configuration, please remember in your mind, here you may have a transistor configuration. Maybe in the next diagram, you will come to know exactly. There are two set of configuration on the transistor part as well as your BJT combination. That means IGBT is the connective combination. If you take the equivalent part of the circuit, you have two NPN transistor back-to-back connected. Along with that, you have a BJT terminal. So all constitute together, you will have an equivalent circuit on the IGBT. That means you have a emitter and you have a collector, and also the bases are connecting in between interconnector. That means you have a gate, you have a collector, and you have a emitter. Please remember, these are the three important terminals on your IGBT. So this may be the voltage and the current transfer characteristics, and the next one is switching characteristics. One is called the transfer characteristics of your IGBT. So the transfer characteristics are considered between your collector emitter voltage and the collector current. The first characteristics may be taken as your collector emitter voltage and the collector current. And similarly, for the second characteristics may be taken as between the collector current and the gate emitter voltage. There are two voltages, gate emitter voltage and the VCE, collector emitter voltage. So between that, again, so I think this characteristic is similar to the previous case, almost like previous case. If you check the characteristic curve, there is no much similar changes. A minor changes you may have on the floor, the drop which occurs on the current side. Please remember. So this may be the switching characteristics. I told you about that because these are all the switching devices will have an ability, depends on the time interval. Based on the time interval or with a small sequence of time delay, we are trying to give a amount of quantum of pulses or a triggering instant to the gate terminal. Thereby your device starts to turn on with the effective function. So please remember in your mind, during this duty cycle, your T on and T on T off value may be calculated. All together will give you the duty cycle ratio. Depends on the duty cycle ratio value adjustment, you can be able to get your delay time, rise time, peak time, and the setting time. I think in the system dynamics, you may have learned about two important states, maybe in the one semester back. Call it as steady state and transient state. And there are systems may be classified depends on the damping or depends on the kind of vibration, or a system may be calculated over damped, under damped, critical damped, and all those things. So all these dampings you may be classified system as first order system, second order system. Same set of transient response abilities have been happened due to the time triggering instant on your gate terminal. Please remember. Thereby only you got the value on delay time, rise time, setting time, overshoot, etc. Please remember. And applications on IGBT like DC and AC motor drives, UPS system, power supply, drives for solenoid relays and the contacts. Please remember. So DC and AC motor drives, you all know about that. DC generator or the BLDC motors, and the AC motor drives maybe like a single phase induction motor, synchronous motor. Okay, so series motor. So AC motor drives, these all the things maybe. I think AC and DC motor characteristics maybe you might be learned in your drives. So you may be have a familiar, and maybe being a robotic student, I think you might be used in your robotic manipulators and robotics manufacturing. I think you may be used about DC motors. Okay, so maybe IGBT you can consider about one of the switching device, and UPS system, uninterrupted power supply system, and the power supplies which are connected in the house. That systems maybe the switching part may be considered here as IGBT. But I told you today commercially many people are looking into SCR or thyristor. And drives for solenoid. What is a solenoid? A cylindrical shaped coil consisting of large number of turns which wound on a non-magnetic frame. That means drives for non-magnetic frames or relays and the contacts. These are all the magnetic properties or the magnetic drives. Okay, the earlier two things are comes under the electrostatics category, and these two, the last one, the third one comes under the category of magnetostatics. The drives for solenoid, being a mechanical mechatronic backup. I think you all know the meaning of solenoid, relay, and the contactors. So these are all the applications where you are trying to use your IGBT with the time delay. And you all know about it. Many relays are available nowadays. Even in the house, you may have a relay. The main objective behind this on and off the relay, right? Sir, no. So please remember me. Just a minute. Okay. So these are the now the comparison on IGBT with now what are all the comparison on IGBT with the MOSFET? So three terminals gate, source and drain, the three terminals gate, emitter and collector, high input impedance on both the side, voltage control device on both the side, then rating available may be differ. One may be 140 ampere 500 volt, and another one is 1200 volt 5 ampere. Always, whenever we go for commercially on electrical or electronic shops, we will tell about the rating, right? We should tell about the rating of a particular device. Rate will tell you about the amount of adequate amount of power which is drawn from the particular device. And also in India, the frequencies are normally 50 hertz. But here we are speaking about all 1 megahertz, 550 kilohertz, all those things are, please remember, switching frequencies. How we derive switching frequency? F naught equal to 1 by 2 pi root of LC. That means your L and C will have a major impact. I told you long back. L is the inductive and C is the capacitive. So inductive reactance and capacitive reactance, when the applied voltage and current are in phase, so that you can able to get your resonance frequency. When the resonance condition met, you can able to attain your switching frequencies. That's why due to the switching frequencies effect only, due to many applications, we are looking into all solid state switches. Now, can you able to get a clear point? Because so long back you will learn the solid switch, you will learn separately drives. But why we have a integration? Because in order to drive the device with much frequencies, in order to get an effective torque and a good output, so thereby a good amount of application, we have to go ahead with the switches on the good switching frequency. Please remember, or we can able to increase the switching frequency. That is the specialty over here. Please remember, whenever any device I have, I may have a time period, I may have a voltage, I may have a current, and all those things. Okay. Suppose if I take an electrical device, I may have a torque, speed, voltage, and current. These are all the basic parameters I may found out. When I go for the electronic, I may able to find out the current and voltage, or in terms of millivolt or milliamps, I may use to get the value. Please remember. So that's why switches can have an ability to change over the frequency according to the requirement on the processor. So thereby, that's why we go for most of the solid state switches based on the semiconductor fabrication. That's why semiconductor fabrications are much vital role in the society. Many semiconductor fabrication industries are looking for physics people and the mechatronics people. Please remember in your mind. I'll stop sharing this slide and open another one. Please be online. Just a minute. And the next one is like firing circuits. For that we go about directions. Okay. Please be online. I'll just open another one. And then next one may be the next one may be what about the thyristor commutation techniques? Already we learned about the thyristors, right? Obviously, how commutation can. There are the two commutation. Please remember in your mind, there are two commutations. See, many things whichever I am discussing here are known by you people, and already you wrote many tests and other things known by you, but still remember, we are trying to brush and we are trying to recollect some of some more collective, additive required information, so that this will help us to go further for the next chapters, forthcoming chapters, in order to integrate with the drives. So that in the later part, I'll tell you how do we integrate the switches, processors, whichever you are learning in terms of a processor, then along with the drives. I think for processor only, for you are learning about some codings or some microcontroller learning or microprocessor on out of the way, you might be learning about Python coding, Java programming, all those things, right? So later part, I'll tell you in what way these are all essential to incorporate all those things together or integrate them together. Now, when we go for commutation, okay, either through commutation, one may be natural commutation and another one may be forced commutation. For the purpose of power conditioning and power control, we are going for commutation. So either to bring back your thyristor from a forward blocking state to forward conduction state. Normally, this commutation may be done by, in order to bring your thyristor back from your forward blocking to a forward conduction. There are two things. One may be a forward blocking and another one may be a forward conduction state. And also, forward current must be reduced to the holding current. These two conditions only, when we met or when we fulfill, we should go ahead with the commutation technique. Please remember in your mind. One may be to bring the thyristor back into forward blocking state to or from forward conduction state. And another one, in order to forward current might be reduced to your holding current. So various amount of commutation. So normally various amount of commutations are there, but being an electrical people, they might be know about why which is a circuit we are supposed to use about this type of commutation and other things. But now, when all circuits are now in the design aspect, when it comes into the whole picture, already the commutation, everything are set by the designer itself. Okay, so now people are not looking for the separate amount of commutation. So at least being people, we should know what exactly the things are happening in commutation. One may be called it as naturally commutated the devices, and another one may be by forcefully, by triggering, by giving an external pulse, or by giving an additional pulse. That's why we call it as forced commutation. One may be self or load commutation, another one due to resonance pulse, third one complementary commutation, and fourth one is impulse, and the fifth one is external pulse. I think impulse word you might be heard it in your system dynamics. What exactly you are speaking about impulse? A sudden flickering on the change of on the signal. A sudden appears on the signal. It will appear for a short period of time and it will vanish. That is called it as impulse signal. Sudden moment within a flickering of sound or within an instant of single moment, the signal may vanish or the signal may vanish. Please remember. Maybe natural commutation. Okay, natural commutation normally occurs in the AC circuit. It does not require any external circuit. Please see the diagram. I have a thyristor, then I have the load. Load is on my output side. Then I have a supply, because here it's a AC circuit. So natural commutation always occurs in the AC circuits. Okay, either two things will happen here. When I have a single thyristor, one may be a turn on and another one may be a turn off. Yes or no? So one may be the turn on condition and another one may be a turn off condition. Please remember in your mind. So this type of natural commutation maybe occurs in your voltage controller, cycloconverter, phase controlled rectifiers. Maybe voltage controllers you may be remembered in order to bring the controller. There are a number of controllers. Controller is a device which is inserted into the system in order to modify the system for a better control action, right? Maybe in system dynamics you may be learned about P controller, proportion controller, integral controller, derivative controller, and combination of all those things, and neuro controller, fuzzy controller, all those things. Similarly, this is another type of controller, compares the signal and it will take an instant signal to modify the error signal in order to go for a better effective way of better control action. And cycloconverters normally used in the aircraft power supplies and other things, cycloconverters. Okay. Then phase controlled rectifiers. Phase controlled rectifiers in order to periodically change the phase. Because in AC circuit, you know very well about the R, Y, and B. There are three phases, right? So in order to control the phases on sequential manner, we go ahead with the phase control rectifier from AC to DC. So here, the commutation occurs only in the natural way. Please remember, and also due to two set of operations, one may be turn on and another one may be turn off. And the forced commutation, we are trying to use it in the DC circuit. Earlier one, we are trying to use it in the AC circuit. Now this one, we are trying to use it in the DC circuit. And this forced commutation requires inductance and capacitance. That means it is trying to reduce the anode current of the thyristor below your holding current. Please remember. That's why it's called it as forced commutation. That means we are trying to reduce the anode current below our holding current value on the SCR or a thyristor. That's why we call it forced commutation. Maybe this application may be used in choppers and inverters. You all know about choppers, right? Fixed DC to variable DC. These all things I think you learned in your SSDC. Okay, anyhow, the later part we'll have a discussion with the choppers and the multi-variable devices. And the self or load commutation. So now here this self or load commutation, maybe self commutation or other ways we call it as load commutation. So two things will be happen. I told you earlier. Only maybe turn on and another one may be a turn off due to the forward and reverse conduction. At the same time, please remember in your mind. So here my thyristor is connected in series with the inductance. My thyristor is connected in series with the inductance as well as the capacitance. That's why it is called it as a self or load commutation. Maybe my load is connected on parallelly across your capacitor. So please remember me on that. So here the specialty is it is called it as class A commutation, and the thyristor is connected in series with the L and C value. That's why I told you last week when we wind up together, I don't know many of you remembered, L and C values plays a vital role on major application, not only in drives, actuators or solid state switches, and also your MEMS microfabrication or micro electromechanical system. I think you people are learning micro electromechanical systems and other things, or being a robotics, some part of MEMS devices. I think you might be learning, right? So please remember, or your signal sensors and signal conditioning areas. That all applications are incorporated together. Maybe the later part I'll tell you how there are like what are all the societal applications which are directly involved on the L and C parameter. How L and C parameters plays a vital role on the fabrication part as well as for the switching devices. Next one is class B is called as resonant pulse. Resonance, I told you, when inductive reactance and capacitive reactance are equal, then we may call it as my applied voltage. When my applied voltage and current are in phase, it is called it as resonance. I think from school onwards, you might be learning about physics fundamental. You might be learned about resonance and all those things, series resonance, parallel resonance. You might learn some laboratory also. Okay, leave it. Now here, your L and C are connected in parallel to your thyristor values. Okay, in your thyristor, the earlier case, the values are connected in series. So here, your inductive value and capacitor values are connected in parallel. Thereby, you are turning on and the turn off the device may happen. Thereby, reduce the anode current to the holding current value. And third one, complementary commutation. So here, complementary commutation, the third one. Earlier two cases, please remember, only one single thyristor you have used. First case, thyristor along with L and C series. Second one, thyristor along with L and C in parallel. And third one, the two thyristors are connected in parallel. Two thyristors are connected in parallel. Therefore, as the gate pulses is applied to the second thyristor, it may turn on so that the other one may be turned off. So that means one thyristor will act at a time. Therefore, the other thyristor will be in operation. The other cases, when it is in turn on, that means gated signal might be considered it to be off. But here it's not like that. When one thyristor is in the conduction mode, and another one might be assumed it has to be the off state or the T2 to be off. That means two thyristors are parallelly connected here. Thereby, you are trying to give the commutation that is called as complementary commutation. Next one is called it as impulse commutation. In this commutation, please remember in your mind, here also this is called it as class B commutation. Class B commutation also consists of two thyristors. Along with that, one might be called it as main thyristor and another one might be called it as the auxiliary thyristor. Along with that, you have a L and C with the diode. Please understand that all the differences, so that only you can be able to remember these things. Otherwise, you do not know what exactly the difference. Some component changes you may have, thereby you are trying to get the required output in order to get the on-state values and the off-state values. So therefore, please remember here, you may have two thyristors like the previous case, but the previous case you may have two thyristors parallel. But here also, you may have two thyristors, but not in parallel. At the same time, along with that, you have an inductor, you have a capacitor, and you have an additional device called diode. So diode, inductor, and auxiliary thyristor forms together, call it as a commutation circuit. And also these devices will act as a capacitive plate or the capacitive transducers. Thereby you can have two set of plates, so that the effective charge will take place between the two parallel plate of a capacitor. And final one is called it as external pulse commutation. That means, you see the diagram, we are trying, this is called it as E class E commutation. or we are trying to give an additional amount of external triggering pulse to my winding effect transformer. See the diagram. I may have a load on the output side and I have an input, and here I have a single thyristor and a capacitor. But what I have a transformer winding. That means in my primary winding side is connected to the gate terminal of my thyristor. But my secondary winding, I have a secondary winding separately. I am trying to give an adequate amount of pulses to my secondary, thereby it may be energized to my primary side, or there is a kind of mutual inductance happen. Therefore, what will happen? A kind of primary current. So a kind of primary current will be flows through to the opposite on the anode current. That means my anode current, my primary current, that combination will be less than my holding current which occurs on my thyristor, so that I can able to make my thyristor to be off. Please remember, just on the reverse operation. That means due to the pulse generation or my external pulses, due to my winding gets triggered or energized or excited, thereby my primary current will be generated. That current will flow in the opposite direction on my anode current. That combination will be lesser than my holding current which is on my thyristor, so that I can make the device to be off. This is called external. That means I'm trying to give a kind of external pulses on the secondary side of my transformer to make the device to be off, or to make the thyristor device to be off. So these are all the various commutation techniques. I'll just stop sharing this one. So these are all the things I'll just, okay, I'll open another one. Just a minute. Now, what are all the firing circuits on the thyristor? So please remember me. So firing circuits, we discussed, right, triggering instant or a firing. So how much of an angle we are trying to give the triggering, or we may have variety of triggering, R firing, RC and UJT. Or normally, when you wanted to increase the time constant of your circuit, we may go ahead with R and RC circuit. I think in your system dynamics, you might be learned about, due to the first order and second order, there is a term called time constant. Tau equal to minus R by L, or minus 0.693 seconds, something like that you might be learned, okay. Maybe forgot due to online classes, okay. So please remember in your mind. So here, we have a three set of firing on my SCR or my thyristor. One might be called it as R firing, second one is resistor, collector combination, resistor and capacitor combination, and the third one unit junction transistor firing circuit. Okay. Now here I may have a small representation on the waveform. So you all know about what exactly a waveform. The waveform will have a amplitude, time period, frequency, and the delay, all those things. Okay. For a complete cycle, I have a 360-degree. Then my frequency might be 50 hertz. That means we all know that how to calculate a time period. So F equal to 1 by T. With that ratio, we will get the time period. Yes or no? So time taken for a complete response of a particular cycle, that is called it as 0 to 90, 90 to 180, from 180 to 270 to 360 is called as a complete cycle. Please remember, 0 to 360 degree together, a complete waveform on the positive and the negative side, that can be taken as a complete cycle. So you can give firing angle at according to your degree. A 30-degree interval, or 45-degree, or 90-degree, or 180-degree, depends on the firing instant we can give. Thereby we can change the frequency and the time period. Thereby the time delay might be. That means the angle between zero crossing of the input voltage and the thyristor, the moment you are trying to instantly give the triggering on the thyristor where you want to exactly fire. That means this diagram will give you a complete cycle, 0 to pi and pi to 2 pi, or 0 to 180, 180 to 360 degrees. Okay, fine. Now, in the first case, we are trying to give triggering, I think 90 degree. For example, I can say that not exactly 90 degree, okay, 45 degree or 50 degree in that diagram. That interval might be called it as the firing angle or the alpha. For example, suppose if I consider 90 degree, it may be like the center part. Between 0 to 180, I may have a center line. From that, okay, I will have a remaining regulator output value. Now, resistance triggering, please remember in your mind, here in the resistance triggering, we may go ahead with the 0 to 90 degree normally. So here I have a thyristor along with the resistance and the diode, and I have a source called Vs equal to Vm sin omega. Since I am speaking about AC circuit, okay, therefore we may have a AC waveform 0 to the 360 degree, or Vm sin omega t. Vm is the maximum voltage and the omega t is the angular frequencies. Omega is nothing but 2 pi f, right? Okay. So here normally the resistance triggering may be the symbol circuit. Maybe during the positive half cycle, SCR becomes acting as a forward bias, and then the other side, in order to when the diode starts conducting, it may act as a reverse bias. But you are trying to change the frequency, or you are trying to limit your gate current by adjusting the firing angle by 0 to 90 degree. So please remember, you might in your R firing circuit or a resistance firing circuit, with the help of a suitable resistance which is connected across the diode, thereby you are trying to control the flow of current by changing the firing angle from 0 to 90 degree in order to obtain your resistance R. So this is how the resistance triggering might be happen. So two things: one may be the source voltage, and another one may be the gate voltage, and the next one becomes the gate voltage. That means your gate voltage is equal to the gate current into the resistance value. Always, as per Ohm's law, what will happen? Vg equal to Ig into R. Okay, Vg is nothing but gate voltage, and Ig is nothing but gate current, and R is nothing but the resistance value. Please remember in your mind. This is how we can able to find out the magnitude of the gate current with the help of a equation. Vgt equal to, or Vg equal to Ig into R. And sometimes, even if your SCR is now conducted one stage, you are trying to turn on with a certain interval. Sometimes with the angular frequency on omega t equal to pi. On the other side, if I turn off my device, that means my device will come back to the original position. Thereby, my switch will be closed. So in first case, my switch might be acting as a open, and another one sometimes SCR may be like acting as a closed switch. When it is in closed condition, what will happen? The load voltage will be 0. When it is in open condition, I can able to find out my open circuit voltage. Got my point or not? With the help of 0 to 90 degree triggering or 0 to 90 degree interval. So see the diagram. This diagram or this waveform will tell you about, see the first diagram, if you say that it is a waveform, Vm sin omega t. Next, that instant of triggering, okay, we have a turn on condition on every interval, like positive half, negative half we don't have. Again, one interval with a positive half. But in the final diagrams, if you see that with a 90 degree firing angle, with a 90 degree firing angle, I have a triggering instant on my output voltage with every positive half cycle. That means my negative half cycle is not working. And so this is maybe the resisting triggering on my resistance triggering. Second one, resistance capacitance triggering. Okay, by the name itself, you can able to understand that I have a two combination. One may be my resistance along with my capacitance, R and C combination values. Okay, so here what is my input voltage? V equal to Vm sin omega t, and my load is connected over here. From through the load, I can able to find out my output voltage. And here, please remember in your mind, I have two set of diodes. Along with that, I have a thyristor. So two diode combination. Along with that, only one thyristor I have with that along with the capacitor I have. That means I have a R and C combination. Thereby, I can able to achieve the time constant for an RC circuit is like minus tau into RC. I think you may be learned in your system dynamics. Minus tau will be by RC. So that means, please remember in your mind, earlier one we just discussed about 0, the firing angle we have given 90 degree. I told you 0 to 90 degree variation. But here, please remember in your mind, the firing angle variation is from 0 to 180 degree. You all know about the cycle. 0, 90, again, 0, 90, 180, 270, and 360. The earlier one is varying from 0 to 90, and here the case is varying from 0 to 180. That means a complete one set of half cycle. That means a complete one set of half cycle. On the positive half cycle as well as the negative half cycle. That means the capacitor voltage reaches to the minimum gate voltage, so that your silicon control rectifier will turn on. The next one, resistance capacitance triggering. Here your capacitor, I told you earlier, will act as the parallel plate capacitor. So one half cycle, the first capacitor will have an ability to trigger the point on the SCR. Thereby, you can able to obtain your RC time constant. And second case, if the top plate of the capacitor might be charged, so that you can able to get the adequate amount of voltage to the reverse conduction on the diode D2. Okay, see the waveform. This might be the waveform on the resistance capacitance triggering. So here you have a sequence of triggering on every 180 degree. That means which is missing. The negative half of the part is missing. In the original waveform, we have a positive half and a negative half. But here we are trying to give the pulses on the every instant on 180 degree. That means the negative half is again missing. That means continuous 180 degree impact on my every half cycle. The first, but the earlier case not like that. My first half cycle, second half cycle is missing, again third half cycle. But here, first half cycle, then third half cycle, and fifth half cycle. So every sequence of my 180 degree, I will have the trigger. And the next one is called unijunction transistor concept. You all know about UJT. Already we discussed about UJT, unijunction transistor. You have a base emitter and you have two bases and one emitter. And please remember in your mind, in order to get the voltage divider value. For example, when we get voltage divider, when I have two resistance which is connected in series, where I wanted to find out my voltage, therefore the voltage source, the resistance which is connected across the voltage source, that value divided by the combination of the resistance. Please remember, whenever I wanted to find out the voltage according to voltage division principle, in order to find out my open circuit voltage, with the help of a unijunction transistor, please remember the condition is the resistance which is connected across the voltage source or across your source voltage, that value divided by the source loop resistance value. Which are all the resistance are connected in the particular diagram will be considered in the denominator side. That means RB1 divided by RB1 plus RB2 into VBB. In this equation, please remember VBB is acting as a source voltage. RB is nothing more. The resistance RB1 is nothing but which is connected across the source voltage. And the denominator term RB1 and RB2 are considered here as the sum of the combination of the resistance value. Therefore, please remember in your mind, with the help of this device, please remember we have a RC combination again. This type of circuits will act as a positive pulse as well as negative pulse. Whenever UJT will act as a triggering device to generate their own pulses, it might be called it as an oscillator. I think you might be learned about oscillator. Whenever I have a weak signal, thereby I can able to trigger my weak signal and convert that one signal to another one, or to generate that amount of weak signal to a stronger one. Then I can look into the oscillator. That means in oscillator, definitely I may have a R and C combination, or L and C combination, or RC combination, or L and C combination. So there is a resistor, inductor, and capacitor. The passive elements will have a major account on my oscillator. So oscillator is a device used to generate signal. So that means here we are trying to generate the sequence of pulses on the negative aspects and the positive aspects. There are various number of waveforms you might be saw it in your linear integrated circuits lab: sawtooth waveform, pulse waveform, triggering waveform, sinusoidal waveform, triangular waveform, trapezoidal waveform. All those things you might be learned, and you might be calculated about the time constant and the value. So time constant will be calculated with the help of R and C value combination. So please remember, so here your UJT triggering will act as an oscillator in order to generate the signal on the sequence of pulses on the positive signal as well as the negative triggering signals, or the positive pulses and the negative pulses. Pulses is nothing but a kind of small signal in order to trigger or in order to generate it. So this diagram may be worked for the speed control. See, even earlier cases, whatever we discussed for SCR or TRIAC or TIAC, everything may be connected to the speed control device. So in speed control device, what you are probably connected, you have a separate UJT circuit with a resistor combination, capacitor combination with the voltage source. In the output side, what you are trying to connect? You are trying to connect a particular motor. Here in the right side, you just see the diagram. I told you in the today's morning class when we started, I told you about load. I told you load in the sense the resistive or inductive or capacity. Sometimes it may be a drive which you have learned. So here I have the load part, we have connected a motor or a output load. Please remember in your mind. So sometimes lamp I can connect, or I can connect a heater. In the house we may have a heater, right? So these all the devices we can be able to connect across the load. Thereby we can able to adjust the speed control of the particular device. Thereby we can achieve the amount of required output. In terms for motor I can attain the speed. For heater I can get the amount of heating which is required. For lamp I can able to increase the brightness and the dimness of all those things. So this may be the UJT triggering waveforms with the full interval. That means here the sequence of pulses on both the cases we have. Got my point or not? Positive pulses and the negative pulses we may have. So this may be the So please remember in your mind. So during this triggering, we can able to change the earlier cases 0 to 90 and 0 to 180 degree cases we have. But here we can give the firing control up to 150 degree with the help of the rate of increase on the voltage source. So up to this, I'll stop sharing. Maybe the previous slide. I think this slide. Please remember this slide. Maybe one more time. I'll give you with some more ideas on tomorrow's class, so that this PPT will be over. Okay. So because three set of applications are there, like motor control, lamp, and heater. I'll tell you some practically how do we think happens. Okay, in the next class. So with this slides come to an end of the firing circuit. So in the next class, I think we'll continue with the thing. I think the first unit almost we are about to end. Maybe tomorrow I'll discuss one more slide, not PPT, one more slide which I mentioned to you. That one we'll have a discussion and we will have a overall design discuss some discussion about the first unit. Then we'll try to give about the introduction part on the second unit, and I'll tell you some of the applications which is relevant to this paper which you are learning, so that only you will also get some interest to learn about this paper. Otherwise, there is no point of learning to online mode or whatever. Otherwise, you will lose your interest, right? So I don't want to be like that. So our class should be an interactive class, so that at least in future you people can develop your own type prototype or module, so that it may be converted as a better work in the towards the society. Maybe the next tomorrow's class, I think we have 2 hours, so that at least we can have a start in the lunch time and we'll have much more discussion on that. But strictly speaking about unit 1, the required amount of all those things are known by you in the earlier class. That only again we have discussed in the 6th semester. In order to know about some, in order to brush up, or in order to know some glimpse of points, in order to know further on the driving part. Got my point? Okay. So please be online. I think today everyone is present. Like I said, I hope it's going to be. Okay. Guys, please tell your attendance. I think little late. Sorry. Okay. Mohit Jain, number 26.
Present, sir.
Yeah, number 27. Saravanan. Guys, little fast. Students are requested to be, because the time is running at a shortage, because the next hour maybe started UP2 11:35 hour. Please respond me as early as possible. Saravanan. Saravanan present or absent? Number 28, Nikesh.
Present, sir.
Number 29, Dhananjay.
Present,
Dhananjay.
sir.
30,
Present, sir.
Arya.
Present, sir.
31, Sanjit.
Present, sir.
32, Sri Darshan. 32, 32. Then 33, Vishnu Roop.
Present, sir.
34, Tarun.
34, present, sir.
35, Jaydeep.
Present, sir.
36, Anshul Mehta.
Present, sir.
37, Mugilan.
37 present, sir.
38, Mohan Sundar.
Present, sir.
39, Nitish Reddy. Nitish. He's absent. Then 40, Manichalvan.
40 present, sir.
41, Muhammad. Muhammad was present earlier. Muhammad, are you in line? 42, Matheshwaran.
Present, sir.
43, Sudarshan Banerjee.
Present, sir.
44, Jashwant.
Present, sir.
45, Suraj Menon.
Present, sir. Present, sir.
46, Ritesh Babu Alam.
Present, sir.
47, Mark Henry D'Souza.
47, present, sir.
48, Sivaguru.
48, present, sir.
49, Sylvester. 49. Pardon?
49 in chat.
Chat, okay. At least remind me, okay. 50, Bharatwaj Srinivas. You people are monitoring, right? At least remind me.
So
50, Bharatwaj.
49 present, sir.
Yeah. 50, Bharatwaj.
So 41, sir.
41, Muhammad Syed. Yeah, I called your name. Okay. Market present. Okay. Then 50, Bharatwaj. Bharat. Okay. 51, Jubin.
Present, sir.
52, Harikrishnan.
Present, sir.
53, Harshita. 54.
54 present, sir.
53, Harshita. Yeah. 55, Muhammad Naim. 57, Subin Babu.
57 present, sir.
58, Parampisha.
Present, sir.
59, Adi Varsha. 59, 60, Vadim Jayashankar.
60 present, sir.
61, Darshan Bharat.
61 present, sir.
62, Vanish Krishna.
62 present, sir.
63,
Present,
Pavan Ganesh. 64, Joel.
Present, sir.
65, Saritesh Vemula.
Present, sir.
66, Hariharan.
Present, sir.
67, Jeeva. 67,
Present, sir.
68, Abhijit.
Present, sir.
69, Samuel.
Present, sir.
70, Hemant. Hemnath. Guys, unmute yourself. Someone is from some house. I am getting the noise. 70, Hemant. 69, Samuel. 70, Hemant. Then 71, Praneeth. Then 71. 72,
Yes,
Raghavendra.
sir.
72.
Yes, sir.
Okay. Then 73, Jagish.
Present, sir.
74, Chandan Shai. 75, Aishman Bhatia.
Present, sir.
76, Shanmukh Shai.
Present, sir.
77, Alok Ranjan Panda.
Present, sir.
Okay, I read the absentee's name. Number 27. They are present. Please respond me to number 27, Saravanan. 32, Sri Darshan. 32, Sri Darshan.
Present, sir.
39, Nitish Reddy. 39, Nitish Reddy. Absent. 50, Bharatwaj Srinivas. 59, Adi Varsha. 59, Adi Varsha. Sorry, Abhi Varsha. 59. Then 69, Samuel Pillai.
Present,
70,
Sir, present.
number 69.
Yeah, sir.
70, Hemant. Absent. 71, Chikil Praneeth. Then 74, Katuri Chandan Shai. 74, Katuri Chandan Shai. So I read the absentee's name one more time. Number 27, number 39, 50, 59, 70, 71, and 74. Thank you. You can leave.